Assalamualaikum, good day everybody. Welcome back to BKU 2333, still in chapter 4 frequency response, and today we're going to discuss about parallel resonance. So hope everyone is in good health today. Alright, parallel resonance is simply a circuit that has RLC and it's a current supply, and this RLC can be written down as transfer function H omega I over B, which is the admittance, or 1 over Z, and it's simply 1 over R for the resistance, J omega C for the capacitance, and 1 over J omega L for the inductance. And collecting the imaginary terms, you'll see that J will have components of omega C minus 1 over omega L. And resonance occurs when the imaginary part of the admittance Y is 0. And doing this, we'll obtain the same omega naught, or the resonant frequency, which is 1 over square root of LC. Now let's try to compare the series RLC and parallel RLC. For the series, we have the impedance as R plus J omega L minus 1 over omega C, and for the parallel resonance, we have 1 over R plus J omega C minus 1 over omega L. And let's try to exploit this duality by replacing R with 1 over R, L with C, and C with L. And we will obtain omega 1 and omega 2, the frequencies involved in the bandwidth, for the parallel resonance as shown in slide. Now compare this with the series resonance, right? And let's look at bandwidth and Q. So bandwidth is omega 2 minus omega 1, that is 1 over RC, and Q is omega naught over B, or omega naught RC, or R over omega naught L, or R omega naught over B. And omega naught L is equal to 1 over omega naught C. This is the bandwidth graph. And these are the frequencies omega 1 and omega 2. Right. For high quality circuits, Q greater than 10, omega 1 is omega naught minus bandwidth over 2, and omega 2 is omega naught plus bandwidth over 2. Now, this is very important because it is a conclusion for the resonance circuits. For the series, we have resonant frequencies for series and parallel circuit which are the same, 1 over square root of LC, and the quality factor for series circuit is omega naught L over R, or 1 over omega naught RC. But for a parallel circuit, we have omega naught RC, or R over omega naught L. For bandwidth, it is omega naught over Q for both series and parallel, and half power frequencies are as shown, and the omega 1 and omega 2 are also as shown in the table. Let's look at an example. You have given a task to design a parallel resonance circuit which will be a radio receiver that operates at 15.9 kHz. Your boss gives you a resistor with a value of 100 kΩ, inductor of 20 mH, and a variable capacitor. Find the value of C that makes the receiver operate at the right frequency. Find also the quality factor Q, bandwidth B, and the half power frequencies omega 1 and omega 2 of the circuit. Now the solution is simple and straightforward. Omega naught is 1 over square root of LC, and but that means you will obtain omega naught is 100 kiloradians per second, and the capacitance is 5 nanofarads, and the quality factor is R over omega naught L. Just plug in the values, you'll get it as 50. And the bandwidth is omega naught over Q. Omega naught we've obtained earlier, it was 100 kiloradians, and that is divided by 50, and you'll get bandwidth is 2 kiloradians per second. Since Q is greater than 10, omega 1 is as shown, which is 99 kiloradians per second, and omega 2 is 401 kiloradians per second. Right. So let's move on to another exercise. Calculate the resonant frequencies of the circuit. So this is a parallel RLC, and in the inductance branch you have a resistor with 2 ohms. So as we know, the input admittance is 1 over R plus J omega C from the capacitance, and 1 over RL plus J omega L. That is the resistance from the branch that has the inductor. So by putting in these values, we can see that it is 1 over 10 plus j omega 0.1 plus 1 over 2 plus j omega 2. And we'll obtain this new equation. And how was this obtained? Was that we multiplied the j omega term with its complex conjugate pair. Now it was actually previously 2 plus j omega 2. So we multiply with 2 minus j omega 2. And we're going to use this later. And at resonance, the imaginary part is 0. So by setting just the imaginary part, we'll have this equation. And by solving this equation, we will have omega naught equals to 2 radians per second. Next exercise is to calculate also the resonant frequency of the circuit. Now it has inductor and capacitor and resistor which are parallel to each other. Now for this, we'll have to solve it for the impedance first. The capacitor and the resistor must be paralleled and added with the inductance. So by doing that, you have this equation, and by multiplying the complex conjugate pair, we will have a new equation which is j omega 0.1 plus 20 multiplied with 1 minus j omega over 100, and that is divided over 1 plus omega squared over 10 to the power 4. And noting that the imaginary part is 0, we'll just take the imaginary terms and try to solve this equation. And in the end, we'll get omega naught is equal to 100 radians per second.